Hey everybody, it's Joe Wachunas here from Electrify Now and NBI. Here with my teammate as always, Brian Stewart. Welcome to our webinar, Cold Climate Heat Pumps, Warm Homes on the Coldest Days. We are really excited about this webinar. We've had our greatest registration for any webinar in our history, so huge round of applause to all of you for coming. And really happy to kick this off. I just want to put a quick shout out there. Folks want to put in the chat where they're coming in from. We always love to hear where folks are tuning in from. So go ahead and throw it in the chat. Let me know if there are any problems with that. So yeah, welcome. We are Electrify Now. If this is your first time on an Electrify Now webinar, we are an all-volunteer organization that believes that electrification is the clearest path to a decarbonized society. And we boil down our electrification message into four easy steps. Number one, clean up your electric supply through solar panels on your roof, community solar, utilities, clean energy plans. Then number two, electrify your home. We're going to be talking about that today, one important part of the home. And we have lots of information on our YouTube page, all of our previous webinars explaining just how to do that. Just Google Electrify Now YouTube. Number three is electrify your ride, be it a bike or a car. Again, a lot of information on our website, electrifynow.net, or on our YouTube page. And then number four is electrify everyone. So huge thank you to everyone who has donated in this webinar or in other webinars to our Electrify Everyone program. This is run through the nonprofit Community Energy Project. 100% of your donations go right to this program where they are replacing old, inefficient gas water heaters with clean electric heat pump water heaters that save families $1,500 and tons of CO2, literally tons of CO2 over the lifetime of these water heaters. We've replaced over 55 water heaters to date through the Electrify Everyone program, and this program has even replaced more through other funding sources. So thank you to all of you for that. A big shout out to our Electrify Coalition. These are organizations, for-profits and nonprofits who believe in electrification and want to help folks understand how to do it. So if you're interested in joining, there's no cost. Just email Brian or I. Our emails on our website. We put them in the chat. Okay, and then a quick shout out to, for our next webinar we've just announced. That'll be on tankless gas water heaters and the infamous methane puff. We have a team from Stanford University that conducted some really incredible science on how gas water heaters emit a methane puff every time they turn on, and this negates some of their climatic benefits. Gas water heaters sell 7 times as many as heat pump water heaters, so we really want to talk about this topic. So join us in January. I'll put a link to the chat in the chat for this registration. All right, Brian, let's dive into our cold climate heat pumps. Why are we talking about these today?
Okay, well, this is a great topic because obviously a lot of people are interested in this, but I think you got to start why we're talking about heat pumps kind of in general, and that's because there's a huge portion of our global emissions that come from heating buildings, and this is information from the U.S. EPA, which breaks down greenhouse gas emissions from various sources, and you can see with this red bar here at the bottom that about 13% of our country's emissions come from essentially heating our residential and commercial buildings. There's a little bit of that which will be from cooking, but it's primarily from heating. So it's a big chunk of our overall emissions, and our own homes are a big part of that, which is why it's important for us to understand the options we have to create zero carbon heating. And there's been multiple studies on this done from tons of different organizations, third-party organizations across the country, that all reach the same conclusion that electrification of our buildings is the lowest cost and the most effective way to decarbonize our buildings. A lot of these studies are regional, but if any of you are interested, this one in the center here from UC Davis is one of my favorites because they directly compare a really high efficiency gas furnace to a heat pump and take long range emissions data from the electric grid and show that everywhere in the United States today, a heat pump will produce far fewer emissions than a gas furnace. And even with the grid in the state it is today. And of course, as the grid gets cleaner, this is going to be more and more the case. So we know that electrification works from a decarbonization standpoint, and we know that these heat pumps work in many situations. But the question that a lot of people will have is, will they work in my area where it's, and everyone experiences cold in the winter, unless you're in the southern parts of the United States where heat pumps have been popular for decades. In the more northern parts of the country, it's a question. Even here, we live on the West Coast. It's relatively mild climate, but even here, there can be this storyline that says, well, when it gets cold, heat pumps don't quite work. But imagine if you're living in, Montana or Minnesota or Maine, and we're going to hear from that a lot about Maine later on today. That question of, working in cold weather becomes really important because nobody wants a cold home. So that's why we're going to dive into this whole conversation about cold climate heat pumps, which are kind of the most high-tech version of heat pumps, maybe, if you want. I love this image from Daikin. But we're going to really dive in with our panelists to what is a cold climate heat pump and how it's different than other heat pumps that we might be familiar with. And importantly, what are the outside temperatures that these systems will operate in? What are good applications for this technology? And how much do they cost in terms of, comparing to other types of systems? And are there special building requirements that are needed in order to make them work? And then we're going to hear very great information from our friends in Maine who have been installing these things for quite some time and have some really good data about how they work there, including information from customers' perceptions. And then at the end, we'll come back to this idea about incentives, because I think everyone is interested in what's happening, particularly with the IRA, around incentives that might make installing these things more affordable. So that's kind of our run of show. I want to introduce our great panelists. We're going to first hear from our first two panelists from Mitsubishi and Daikin. Sean Lamons is the Performance Construction Manager at Mitsubishi Electric Trane, and specifically focused on HVAC and efficient cooling and heating systems for residential new construction. He has tons of experience in this area and multiple certifications. I've only listed a few of them here because there are too many to fit on the page, but basically suffice it to say he's got a lot of experience with ways of measuring building efficiency. And since 2009, he's been completed analysis of over 6 million square feet of residential and commercial buildings. So he's got a wealth of knowledge on this exact topic from a practical standpoint. And then we have his kind of colleague competitors, but they're friendly competitors. I can tell you that from having worked with them both. Both really great guys, and I think they respect each other because we're really talking about the two market leaders here, Mitsubishi and Daikin. I kind of like to tell people that Japan has been at the epicenter of development of the modern heat pump, and their climate includes some very cold spaces. So it's no coincidence that they've created products that really work for Japan and then obviously around the world. Jonathan is the business development manager for Daikin North America, and he's a nationally regarded expert in residential contracting and heat pumps. He's also a co-owner of the Heat Pump Store, which is one of our members in the Electrify Coalition, and a great organization here in Oregon that's installed thousands and thousands of heat pumps, primarily focused on ductless systems. And this is a great kind of like double we have with Jonathan, because he's got experience on the installation side and also from the manufacturing side. And so those are our two manufacturing partners who are going to be talking today. Then I want to introduce Laura Martell. She's the Research and Evaluation Manager from Efficiency Maine. She'll be kind of bringing us home with more real detailed information on application of this technology in a very cold part of the country. Efficiency Maine Trust is the independent administrator for programs that promote energy efficiency, alternative energy resources, and carbon savings in Maine. Here, the equivalent is called the Energy Trust of Oregon, but in many states, there are these organizations that really promote energy efficiency, and they drive these big programs where you can get a lot of really good detail and data. Laura has more than 18 years of technical leadership and project management experience, researching and evaluating these applications of heat pumps and other technologies. She's got a BS degree in ocean engineering from Florida Atlantic University, so I'm not quite sure how she ended up in Maine. Maybe she can tell us that later. And she also has a master's of engineering in acoustics from Penn State. So first of all, welcome and thank you to our three panelists. You're going to hear first from Sean and Jonathan. So I'm going to stop sharing my screen and turn it over to those two to get us started.
Well, and while they're getting those loaded up, folks, please put your questions in the Q&A and leave comments in the chat. That's the easiest way for us to filter. So yeah, turn it over to you guys.
All right. Grab this screen here, and I think we should be good to go. Let's see. Of course, little delay. There we go. You guys see my screen?
Yes.
All right, perfect. Thanks so much. Appreciate it, Brian. Appreciate it, Joe. Jonathan, you and I are going to have a little conversation around some of this stuff. We've got about 15 slides or so. And so we invite people to ask questions. I think we're going to take a little bit of question and answer right at the end, and then hand it over to Laura. So we're going to dig in. What are cold climate heat pumps? Short answer is cold climate heat pumps are designed to work in cold temperatures. I know it's a hard sell there. You know, it's a brainiac moment there, but we want to talk about some of the specifics here, obviously. Some of you may have heard about the polar vortex that hit Chicago a couple years back, a few years back now. These are screenshots from a video I took when I was up there with a colleague. These heat pumps were operating when the high temperature, the daytime high temperature was negative 20 degrees. So it was negative 20 or colder for 3 days in a row. Systems are up and running. That's a cold climate heat pump. Another example, more of a high elevation example. So to dispel the worry about higher altitude and air density and such, questions about that. But this is a field test up in Aspen ski area, Snowmass ski area. And this is at the patrol hut and warming hut at 11,300 foot. And just this past December, they had the biggest storm in 43 years with 100 inches of snow in December, and 66 inches of that happened in 9 days. Yes, this system has had some challenges at these extreme conditions, but throughout the year, as long as the system is operating properly and the snow is cleared away, they have been able to turn off the electric resistance breakers in this building, and it's handling the heat for this life safety building. So I'm going to hand this over to Jonathan. So Jonathan, what's your opinion of a heat pump, and where do we go to find out information on this?
Yeah, thanks, Sean. And I love being on the same presentation with you. This is a real treat. Thanks to Electrify Now for getting me and my buddy Sean together. I always learn a ton from Sean, so he's one of my most valuable, friends in the industry. Beyond the fact that, yeah, we have lots of experience with these heat pumps working, how would a consumer know, and how would someone shop intelligently for a heat pump? And there are standards that you can draw on, although the definitions that found in these standards kind of differ depending on who you ask. So like utilities and government programs rely on something called the NEEP cold climate list. NEEP stands for Northeast Energy Efficiency Partners, a regional energy efficiency organization that has really pioneered this standard setting around a cold climate heat pump. Soon, start of the year, Energy Star will also start defining cold climate heat pumps, and their standards align, if not nearly exactly, pretty close to exactly with the NEEP standard. Now, manufacturers like Mitsubishi and Daikin have brand standards around cold climate heat pumps, something a little bit different. Mitsubishi produces a brand called Hyperheat to identify their cold climate heat pump products. Daikin has Aurora, Panasonic Exterios, and I could go on and on and on through very successful and reliable brands that are in the marketplace. And I think for most of these manufacturers, the brand standard could be a very useful way for a consumer to identify a cold climate heat pump. Sean and I conferred in creating this content, and we think some people feel that if a heat pump, a modern heat pump, uses variable capacity or inverter technology, that this by definition makes it a cold climate heat pump. We don't agree. And so we have a few other additional things that we'd like to throw out, which we think define a cold climate heat pump. So with that being said, let's dive into it. There are a few key metrics that most groups, including the brand standards that Sean and I's company have created. And let's just review these really quickly. To sell products in the US, we have to go through a rating process, and 47 degrees Fahrenheit is a standardized rated temperature, and which we have to produce a number for. And so this is one of the important things, but for cold climates, like 47 degrees isn't that cold. And so it's perhaps not useful, but it is a number that becomes important, as you'll see in a minute. The maximum performance at 5 degrees is a really important metric for cold climate heat pumps. At 5 degrees, we are cold. And the total capacity of a heat pump at that, the maximum performance or total capacity, is a really important, useful number. Most manufacturers, at least in their technical brochures, produce these numbers for consumers to look at. And at the end of the day, a consumer buying a heat pump, you're buying a heating appliance, and knowing its total capacity at 5 degrees can be really, I think, a useful number. Although the needs of the space, of course, will make that number most relevant. And so you need to know that piece of information to really put that maximum performance at 5 degrees to use. There's a ratio of numbers 1 and 2, and this becomes really important to a lot of programs. They want to see this ratio of performance be really high. And so for Daikin and Mitsubishi, our brand standards are nearly identical. Our brand for cold climate says we will have 100% of the rated capacity still capable and being produced at 5 degrees. And so I think that's a really important number. NEAP and Energy Star have a much lower number. And Sean, I think we're in agreement, right? That we think that 100% is really important and useful. Finally, moving along, coefficient of performance. This is an energy efficiency measure. To put it most simply, it's the amount of heat output as a ratio of the amount of energy used to produce those heat. And it's a really great number. Heat pumps, really great cold climate heat pumps, produce coefficients of performance at 2 or higher, down even well below 0. And the NEAP and Energy Star standard is actually below 2 at 5 degrees. And yeah, it's not super rigorous, but it's still very efficient, and it's an important number. Now, finally, and this is something both of our brand standards conform to, is publishing rated performance of heat output at very cold temperatures. Each brand's a little different. Sean and I both work at companies that will mostly use -13 as our published performance floor or bottom. But some of our models, we actually, at Daikin, we produce down to -15. One of our competitors produces down to -22. When you're really cold in climate zones 6 and 7, those numbers become really important for heating contractors too.
I'll add into that too. It depends on the model. I think all manufacturers that produce high quality will have a range of maximum low temperature operation. Guaranteed operation is terminology. But just to move along here, this is a bit of an eye chart on, depends on who you ask. What is a cold climate heat pump? Whether it be programmatic in the first column, whether it be brand opinions in the middle column, and in the right column, Jonathan and I had some ideas about, what does this really mean? Yeah, we agree that performance at 47 and 13 and 5 are numbers that need to be looked at. But I underlined capacity at design temperature. And I think that's a really key piece. So rather than just looking at the capacity ratio, which is a tested metric that you're going to see in cold climate equipment selection, It's really important to work with skilled HVAC designers or professionals to look at what is the capacity of the system at that design temperature. Is it going to do the job, deliver the heat to meet the heating load for the house for comfort specifically? And a key piece there is looking at equipment that is purpose built for cold winter comfort, right? That's this additional criteria. I also want to point out that the negative 13, that relates to, I want to say, I don't get this wrong, but I think it's negative 25 Celsius. And so looking at that is a test metric number, not a limitation necessarily. The equipment, many of the pieces of equipment will operate much lower than that. It's not a tested and published number. So moving on to a little bit more on the additional criteria. I'm not going to go through all of these items necessarily, but just thinking about what sets a cold climate heat pump apart from a standard heat pump. It's going to be looking at possibly the inverter compressors, and the motors that go into this, and the efficiency of use over time, rather than this on and off cycle that you see with typical 1 and 2 speed systems. Looking at the programming, the algorithms, how does this system handle these patterns? And one key item is looking at a hot discharge air temperature and just right airflow for matching up, the need with the capability. And the looking at defrost cycles and the defrosting of the drain pans, various small pieces of equipment and logic that goes into the equipment, optional wind baffles, and other design options that can be applied by skilled HVAC designers, skilled contractors, working, even getting training and knowledge from your distributors and the manufacturers, because these are the folks that are working with this equipment and understand maybe the deeper dive details on this equipment to properly apply them in your situation. Go ahead on this one, Jonathan. I like your take on this.
And it's worth noting too, like through our experience at the heat pump store, like 20,000 homes, even a stated cold climate heat pump is not always really excellent in all the ways that Sean just illustrated on that slide. And so, looking at reviews, talking to people who have a heat pump in a cold climate, like Maine, for instance, not all cold climate heat pumps are alike. And that's the point I wanted to take away with, is maybe getting some opinions on people, how they have to maintain it, if at all, how they had to adjust it in extreme weather, if at all. Those are good indicators. So yeah, moving to the next slide, Sean. Where are cold climate heat pumps used? This was a particular conversation point that Brian and Sean and I had in preparing for this presentation. Sean and I believe that this climate zone map can be a little misleading for people. Cold climates are typically in areas which you see as 5, 6, and 7 on this map. And there are 8 and 9 and 10 up in Alaska and Canada, of course, too. But for this map, 5, 6, and 7 are the traditional kind of cold climate areas. And one would think, well, that must be where these cold climate heat pumps are best suited. And I have found through my experience living and working in climate zone 4 that we love using cold climate heat pumps, again, because they are purpose-built to make heating comfort and be easy to operate in inclement weather. And when you look at the black line that I drew on this map, it's kind of this long-standing heat pump business that above that line, roughly, more of the equipment hours of operation in a year are spent heating. We call them in the HVAC industry a heating dominated area or climate. And in my mind, anything above that dotted line, certainly in climate zones 4, is probably a great location for a cold climate heat pump. Not because you absolutely need it, but we think, it's going to give you so many of the features, benefits, and comfort aspects that will give you a great experience with a heat pump. Area below the line, more time spent cooling. And at that point, yeah. So I think you're up next, Sean.
Yeah, sorry. Didn't mean to jump ahead there. Well, just looking at some guidelines, right? So to summarize, heating dominant climates, frequent snow and ice and maritime climates in, thinking about cold rain and fog, that could be, upper Northeast, Northwest, etc. And then thinking about a few guidelines. Think about wind direction. These pictures are kind of small. I apologize for the eye chart here, but thinking about wind direction, thinking about drainage of water, where does that cold condensate water in the winter come out and possibly freeze and cause hazards that you want to avoid? And then also measures for snow, whether it be snow baffles or watching out for drip lines and roof lines, or just fully covered under a deck or something along those lines. All considerations for good cold climate guidelines. And then looking at this chart, and it's a pretty simplified chart, but it does get the point across that a standard heat pump in the blue line there versus a cold climate heat pump with the red line, and that red line, from our perspectives, for our manufacturers, we're looking at 100% capacity at 5 degrees and starting to stretch into that those negative numbers on full capacity, and then that tapering off and that broadening range there at the left side. That really depends on the model that you're talking about. The good, better, best, the features that it comes with, which model are you looking at?
Sorry,
Now,
Sean, can I jump in on that? Because I think that slide is really helpful. I mean, in the standard heat pump line there is important, because basically what that's saying is that as the temperature gets colder, the heat pump is able to produce less heat. And that can be a real problem if your home needs more than those numbers of BTUs that it's putting out as the temperature gets colder. So because if you had a line that showed what the house needs, it would be a line angling up from the bottom, lower left, lower right, going up, right? Basically, because it needs more as the temperature. So I don't know, can you just chat on that a little bit? Because that's an essential part of this whole load calculation thing that a good HVAC installer is going to be doing, right?
Yeah. So as the temperature drops, the heat demand goes higher, but with a standard heat pump, that it's an inverse relationship. As the temperature drops, it's less capable of delivering heat into the house. And so that can be great down to that 40 degrees, 30 degrees, 20 degrees type of range. That could be a decent matchup with a dual fuel system consideration. And that's probably where we're going to see a lot of expansion in the heat pump market, is that dual fuel application, so that another heating system, whether it be a natural gas furnace or other that is tied into the control system, can take over and start to heat that house as the temperature drops. That is a viable pathway that we as an industry see significant growth in. And just know that between these two lines, there's a range of equipment that fall, either above or below whichever of these lines we're talking about. These are just generalized explanations of cold versus standard heat pumps. So it's going to depend on the model you're looking at, and the NEEP cold climate heat pump list is a great way to look at that. We're not going to spend much time on that today, but I'm looking forward to Laura's information as she explores that information. I'm gonna take the risk of a slippery, wonky slide down the technical hole here. What I want to point out with this slide is to demystify how a heat pump works real quick. The blue side is low pressure. The orange side is high pressure, if you will. The compressor in the middle pressurizes that refrigerant to deliver heat inside. And as that refrigerant goes back through that expansion valve, depressurizes, cools off, it can now absorb the energy that's in the air on the outside, and then just gets recompressed and pushed back in. So it is a cycle that holds onto the refrigerant, and it just manages temperatures and pressures of that refrigerant to absorb heat out from outside, deliver it inside. And by the way, this is how any air conditioner works in reverse in the summer. So that's as geeky as I'm going to get on that for today. Go ahead, Jonathan, on this one.
Yeah, but it's a good teeing up to like this slide where we try to show you how these cold climate heat pumps actually achieve this magic. It's that in the earlier slide we saw how they can maintain performance as temperatures drop, and in that previous slide we saw how the refrigerant cycle works. Cold climate heat pumps have these whiz-bang technology, for lack of a better word, like variable speed compressors. As it's cold, the compressor can work harder and move faster. The fans can do the same. The expansion valve is electronic, it's not fixed. And so it can fire faster to change the pressure to an incredible exacting amount. And of course, there's a very intelligent computer with an algorithms and lots of programming specific to cold climate operations that make all of this happen. But you might not notice all of these special components and programming from the outside because these machines don't look really very much different. Now, because the heritage, the technology came from Asia to begin with and Japan really to start with, they are small compact units that are what we call side discharge. And whereas in America, most air conditioners and heat pumps are cube-shaped and rather large, we have more space, and it's just what we had developed technologically over time. So cold climate heat pumps, really, you might have two side discharge machines, and they wouldn't know if one was cold climate or the other, except for maybe some branding on the outside. And yeah, moving to the next slide, the cost then becomes, I think, the next question that most people ask us. I think because of some of the special features and programming, typically you can expect a cold climate model to be 20 to 30% more for the equipment cost compared to a non-cold climate model. But I'd like to point out that when you buy a heating appliance and heating and cooling appliance, you're paying for the ability of that machine to make BTUs. And in my experience, looking at lots of performance tables of these units over the years, I found that the amount of heat produced by a cold climate model is much more. And so dollar spent per BTU created, I think that the cold climate heat pumps ultimately become a better value. I'm speaking in generalities here. Every model is a little bit different, but in my experience with frankly, with the brands that come out of Japan that I've been most familiar with over the years, I can say that this can be the case for cold climate models.
Yeah. And along with that, there's so many choices and so many details. And as these things get more complex, it is a challenge to identify the details. So I wanted to point out a little bit, some teachable moments here. On the left side, we've got, I just saw this last week, actually in Spokane, Washington, doing a visit, and 4 systems on the wall. 3 of the 4 do not have any kind of condensate management. The top 2 are dripping down towards the bottom 2. The one on the right, top right, actually has a pan that's going to drip that refrigerant out past the lower unit, and clearly there's less ice buildup on the one that's the bottom right there. And I sure wouldn't want to live in that or sleep in that bedroom that those are attached to. That would be a little bit rough, I think. Some other items in here. Looking at, if you've got frost on the indoor coil, there's a good chance you're looking at a cross-wired system where the communication and the refrigerant flow are not aligned to the proper, they're not lined up in terms of, indoor system 1 is not necessarily receiving the right signal or the refrigerant at the same time. So indications of an issue. The line sets, both line sets need to be insulated. So on this image right there, that line set is, that smaller line set is not insulated. That's the refrigerant piping that goes between the indoor and the outdoor. And then a few other items about airflow, making sure you've got good airflow around the outdoor units on the right side, a tall fence, tight space, maybe not lifted up off the ground for clearance for ice and snow buildup, etc. All considerations. And then also dust and debris, maybe during construction or remodel. It's hard to see in that image, but that fan, I'm looking inside a unit and taking a picture of a fan, and you can see a swipe of my finger across that fan, just removing a bunch of dust. And that's really hard on the coils to make them operate long-term properly. This is an article from Green Building Alliance. The issues here, we're not going to go through them, but it's a great example. If you want to check it out, go read it up. It's an interesting kind of natural case study, if you will, of what were some of the challenges, what were some of the things that were done, what were the outcomes and the causes of those outcomes. And there's some good discussion in that on that article about oversizing, about correct heating and cooling loads, or thinking about humidity management, over zoning, how many pieces of equipment are inside this house that where the insulation, the air sealing, and the windows have been improved and the loads have dropped. It's a great discussion about some items to think about and the details that do matter on that. And as we finish up here, I want to point out we've got massive work ahead of us as a country and as a world. And so we want to remember, I just like the concept of, perfect is the enemy of good, per Voltaire a while back. And an updated version, perfection is the enemy of done. So we've got a lot of work to do. It doesn't have to be perfect, but we do need to pay attention to the details. And rest assured, we can get this done. These 14-year timeframes from 1935 and 1955, we got a lot of really important, valuable, long-term work done in short period of time. And I think we can do that as a country and as a world. So thanks for the opportunity, everybody.
Yeah, thank you so much.
Yeah, thanks guys. Brian, I'm just wondering, looking at the time, if we want to go right to Laura.
Let's just go straight to this. I think that was really useful. I think I asked the one question I really wanted to in the middle there, but let's go to Laura, and then we can come back with some general questions I think maybe everyone can answer.
Yeah.
Thank you, Laura. Laura, you're on mute there.
There we go. It did not want to take me off mute for some reason. Hello, everyone. I'm Laura Martell from Efficiency Maine, and I'm going to take you through some slides of some of the heat pump activity that we have had in Maine. So I wanted to start off just showing you what we've done in the past 5 years. Our fiscal years run July to June, so that fiscal year 2022 just ended this past June. Between 20 and 21, our governor announced a heat pump challenge to install 100,000 heat pumps by 2025. And Efficiency Maine responded to that by restructuring our program and offering some enhanced incentives. And you can see we more than doubled our program activity between 2020 and 2021. And we are on track to not only hit that 100,000 heat pump challenge, but to blow it out of the water. So we've been doing this for a while. We did our first round of residential heat pumps back in 2012 with a handful that went into low-income multifamily buildings. So we've been at it for a while. A little bit of the background on heating in Maine. So Maine is a oil-dominated state. We have in existing homes the highest penetration of oil heating, I think, in the country. And so this is 3 different studies looking at 3 different time frames. The 2008 study and the 2021 study were both looking at new construction that were completed within 3 years of those studies. And the 2015 looked at all of the existing housing stock in Maine. So that was, we had homes from the 70s and the 60s included in that assessment. And I'll draw your attention to the large orange that you can't possibly miss in the left and middle charts that is almost non-existent in the chart on the right. Oil boilers in particular are fading in new construction. And one of the things that's replacing it, in fact, probably the largest, fastest growing aside from propane, which is a whole other discussion, is heat pumps. So at the top there in the gray, red, and dark blue are the heat pump contributions. So the red is heat pumps alone. So no other heating source in the home aside from heat. Blue is heat pumps with an electric resistance. And actually the other heat pump one is that green bar, which is having a furnace, propane furnace along with a heat pump. So 20% of homes in Maine that were built between 2017 and 2020 had all electric heating. Most of those had just heat pumps, and the other ones had heat pumps and electric resistance And when we say electric resistance, generally what we're talking about is either a backup element in the air handler or some small sections of electric baseboard in odd spaces like bathrooms or back rooms. So a little bit about cost and what we have seen in Maine. So for a new construction home, the cost to put in a boiler is around $11,000. That includes all of the distribution, so the piping, the fins, the radiators, all of that. But it doesn't include any cooling, where the cost of a heat pump system, which is made up of ductless units. So these are the units, when we're talking about cold climate heat pumps, that's often what we're talking about. It's an outdoor unit with an indoor unit. Sometimes there's one outdoor unit to multiple indoor units, but we're talking about a non-centralized system where we have individual air handlers in specific rooms to provide the distribution of the system. And it's the refrigerant rather than air or water that is being moved around to provide that distribution. So the cost for that is around $13,000. The difference is about $2,500. And as I mentioned again, the boiler doesn't come with cooling. So if that home requires cooling in addition to heating, that is going to be an extra expense that needs to be added to that boiler solution. And the chart on the right is showing the operational costs of heat pumps versus a high performance heat pump. The high performance heat pump is the green line. The blue line is a standard efficiency heat pump. And I'm using national average costs here. So the cost of electricity is just under 16 cents per kWh. The purple line is natural gas based on $2.56 per therm. So that would be like a natural gas boiler or furnace. Oil is the red line at the top there at $5.46 a gallon, and propane is the blue line in the middle at $2.66. So you'll notice that the natural gas, oil, and propane are flat lines. They're horizontal because it doesn't matter what the outdoor temperature is. Every BTU that gets produced costs the same amount based on the fuel costs. Heat pumps are a little bit different, right? You saw the chart that was shown before that showed that the efficiency of the heat pump drops as the outdoor temperature drops because it's trying to extract heat from colder and colder air. And the colder the air gets outside, the harder it is to extract that heat. That causes the coefficient of performance to go down, which means that it costs more. You have to use more electricity to produce the same amount of heat at those colder temperatures, and that's what creates these curves. And I would draw your attention to the intersections of those curves with the horizontal lines. Each one of those intersections is the point at which the outdoor temperature, which is the x-axis, the outdoor temperature at which the heat pump below that costs more to operate than the comparative system. And above that, the heat pump costs less. So there's a couple of things to point out here. One is that those crossover points happen down below, close to or down below 0 degrees. So we're talking cold. This isn't just chilly. This is cold temperatures. And so it looks like there are going to be times of the year where you'd be better off running your oil boiler than your heat pump. Well, not your oil boiler, because that one goes off the chart entirely. You'd have to be down at minus 25 or minus 30. But let's say for propane, right, there are going to be times of year when it's less expensive to operate your propane boiler than your heat pump. But there's some more to take into consideration. So I'm going to take you through a couple of charts here. There's going to be a bit of a buildup. Bear with me. I think the ultimate conclusion will be worth the trip. So I'm looking at Caribou, Maine. For those of you not familiar with Maine, we're the northeastern state of the Northeast. We are the furthest north New England state, and Caribou is in the northeast section of Maine. It is not the furthest north town in Maine. I noticed that there was somebody on the webinar here from Fort Kent. That's even farther north, but Caribou's way up there. It is USDA hardiness zone 4B and 4A, which means aside from growing potatoes, it's really hard to grow anything up there. It's really cold. IECC zone 7. So that's the purple that we saw on those charts before, right? The coldest of the continental contiguous states. And there's 8,760 hours in a year. Of those, 6,444 of them are at or below 60 degrees in Caribou, Maine. So over 6,000 hours in the year require heating. And that works out to, when you look at the actual temperature differences, to be over 8,000 heating degree days. So it is cold. It is a very cold climate. And on the left side, what you see is a cumulative chart of the hours in the year that are at or below the outdoor temperature that's being displayed. So if you look at 0 degrees, there's about 500 hours at or below 0 degrees. So why am I going through this? Why do we care? Well, remember those crossover points, right? So if I take the temperatures at which those crossover points occur, and I zoom in on the chart and I look at those cumulative hours, you can see that natural gas, the crossover points around -3 degrees, there's 300 hours or so that the temperature is below that. Well, that's 5% of the heating hours in Caribou. It's not a lot. And for propane, where that crossover happens at -9 degrees, it's only 1%. So as cold as Caribou is, that crossover where you would save money to run your traditional system versus a heat pump system, it's actually a very few number of hours. They normally happen in the middle of the night for short durations. And I would not recommend anybody sitting next to their thermostat trying to time switching between systems. And even if it's automated, it's just not worth it. And I'm going to try to convince you that with this chart here. So the bars or the columns on the left chart are the annual operating costs for the various heating systems. So in red is the heat pump, in green is natural gas, a boiler, purple is propane, a boiler, and oil is the blue, also a boiler. So you can see that the heat pump is the least expensive system to operate. And this is assuming heating the whole home all winter long in Caribou, right? We're still talking about Caribou. In the middle there, you see the cost difference between operating those other systems and a heat pump. So if you ran a heat pump rather than a natural gas boiler, you would save $1,000 a year. Against propane, it's about $1,600, and against oil, it's almost $3,400. What if you were sitting by your thermostat and trying to time exactly when your natural gas boiler was less expensive to operate than your heat pump? You were going to squeeze every last nickel out. If you got it perfect, you would save an extra $26 a year. It's immaterial. So, and this is really important because we're trying to bust a myth that is out there that you need a backup system and that the backup system has to come on at temperatures well above these cutover temperatures that I just talked about. And I've heard recommendations of 20 degrees, 30 degrees, and switching back over to your old system. With the current costs of energy, it doesn't make sense. It just doesn't. There just aren't enough hours to make it worthwhile to switch. This chart here, switching entirely, this is no longer Caribou. This is another myth that I'm trying to bust, which is we have been told for many, many years, decades, that to save energy, we should turn down our heating systems when we're sleeping. And I'm here to tell you today, for heat, it works great for boilers and furnaces. By all means, keep doing it. It's more comfortable to sleep when it's cooler. You save energy. You can just put an extra blanket on the bed. Go for it. With heat pumps, I wouldn't recommend it. And the reason why I wouldn't recommend it is because of the results that I'm showing here, as well as some results that I'll show in some of my later slides. So this is exactly the same configuration of a home run in two different ways. So they ran it and there's 2 heat pumps in this home. The red one's on the second floor, the blue one's on the first floor. And the line there is the heating degree days. So in the configuration on the left, they picked a comfortable temperature and set it and left it. They did not adjust the thermostat in that home. You'll see that the first floor heat pump carried almost all of the load of the home. It was able to satisfy the indoor temperature request through all months with very little second floor heat pump use. On the right-hand side, they were turning off the heat pump at night and turning it back on in the morning. And what you'll see, not only does the second story heat pump have to contribute a lot more to the heating load of the home, but when you look at the sum of both heat pumps, you're looking at almost double the energy use by turning back the temperature at night and turning it back up in the morning. And like I said,
I would just add that this has been game changing in my family, because I for 10 years I've been turning off our heat pumps at night. My wife is so thrilled that, you know, electrification means more comfort, more heating out. If you're more efficient if you run your heat pump all the time. So that's amazing, amazing stuff.
And so now I'm going to jump into some evaluations and studies that we've done in Maine. So the first one is our Home Energy Savings Program, HESP. We did an impact evaluation back in 2017. We looked at homes that are projects that had been completed in the 2 years previous, and we put meters in the home, and we did participant surveys, and got some good data on heat pump usage and heat pump performance in Maine. So the first thing is just satisfaction with heat pumps. So there were actually 2 programs that participated in this evaluation, the Home Energy Savings Program and the Affordable Heat Initiative, which is an income eligible program. So we looked at the results of the survey, and you can see there's 6 different categories here on their satisfaction. On a 1 through 5 scale, how would they rate these different components? And you can see they're all really high, and both of the programs were really consistent. Folks are really happy with the heat pumps that they've had installed. And I think that's great. But I want to show the next slide, which shows the usage of the heat pump. So this is measuring the kilowatt hours that were used by the heat pump for a typical year. And all of these bars, each one of them is a home that participated in the study that had good meter data that we could analyze. And it goes from those homes that used the least amount of electricity to those that used the most. And I will point out here that this is not a case of less electricity is more efficient and therefore good. Because if you remember the previous slide where I showed you that heat pump is the least expensive way to heat your home, what's happening in these homes is they're using a heat pump and something, a heat pump and a boiler, a heat pump and a furnace. So the homes where they're not using the heat pump much for heating, they're paying more for the heating than those that are using the heat pump more. So in this case, more usage, the more you use it, it's like a sales pitch, the more you use it, the more you'll save. And that's absolutely true with heat pumps. And so one of the things that Efficiency Maine has been working on and continues to work on is trying to figure out not just how to get people to adopt heat pumps and put them in their homes, but how to actually adopt the use of heat pumps and get more out of their heat pump every day, all winter long. So now to another study. So this was existing homes where we recruited homes that used heat pumps solely or primarily as their heating source. So these were folks, these are early adopters that decided that they wanted to be an all-electric home or close to an all-electric home, and they installed heat pumps for heating. There were 10 homes that participated. 7 of those 10, during the metering that we did in February through June of 2021, didn't really use any other heating source. Most of these homes retained their existing heating source. So they had boilers, they had furnaces, but 7 out of 10 homes, it was not significant, the amount of backup heat that they used. And again, these are homes in Maine. We asked how satisfied these folks were. And I've got some quotes there on the right. I will momentarily be quiet for a little bit so you guys can actually read those quotes. But again, we saw the same thing that we did with the home energy savings program. Lots of satisfaction. This is each individual home that participated and actually responded to the survey. And I put a couple of, it's always good to have balance, right? So there's some really great quotes here. And then there's a couple at the bottom. Might call the manufacturer's attention to it. There are challenges, just like with any heating system. So we dug a little bit more into the satisfaction and we asked the folks why they were satisfied, what drove their satisfaction. And you can see here, this was a multiple choice response. You can see what drove their satisfaction: reliable performance, increased comfort, low operating costs, quiet operation, easy operability, which is funny because of the one person who said the controls are terrible. Guess it depends how tech savvy you are. And then again, there's some quotes there. I'll let you guys read those. And I think the one on the bottom is so funny. Their neighbor didn't like their outdoor unit, so they started blowing snow into it. Okay, so this is some meter data. Actual usage. This is a home in Gardner, Maine, which is kind of right in the middle of the state. So not the coldest, it's not Caribou, but still pretty darn cold. This was some metering done in February. You can see the blue line is the outdoor temperature. You can see, every night it gets cold, it starts to warm up the next day, and then it gets cold again. The red is the indoor temperature. You can see that it mostly stays steady, but there's some dips. I'll talk about those dips in a moment. And then the gray bars there are the electricity use. So I'll draw your attention to a couple of key parts of this chart, right? I mentioned there's the red line, the indoor air temperature, where it dips. That is setbacks. This home had a thermostat that had an automatic program in it that set the temperature back every night and then recovered every morning. So what you're seeing is the home is just plodding along right around that daytime set temperature until it gets to the point where the temperature is set back. And then the home drifts down. So that drift, the angle of that drift, is dependent on how well insulated the home is. Poorly insulated, drafty home, that's going to drop a lot faster. Tight, well-insulated home, that would actually drift a lot slower. But that's what you're seeing there. That's why that indoor temperature takes a dip. And then when the system sort of wakes back up and says, oh, we need to go back up to daytime temperatures, you can see it climb. And you can see it climb fairly slowly. Heat pumps are slow heat. They're not fast heat, right? It's like slow money and slow food. Sometimes it's good to wait for things. So heat pumps are slow heat. They're not a furnace. They're not going to blast you with ridiculously hot air. They're just gonna creep up the temperature over time. And the gray bars, as I said, is the electricity use. And what you see is during the day, when the temperature is being kept steady, you can see that the heat pump kind of bounces around. Needs a little bit more now, a little bit less, a little bit more, a little bit less. When the setback happens and the house is allowed to drift, the use goes to nothing. It goes to idle, standby, right? You can see that dip there in the gray bars that corresponds to the dip in the red line. But then what happens the next morning, probably really early in the morning, right? As you can see here, somewhere in the 2 o'clock range, 2 a.m., the system says, oh my goodness, we have to get back up to temperature before 7 o'clock in the morning. And it kicks on, and it kicks on hard, and it kicks on during the coldest hours of the day. And remember, heat pumps are less efficient the colder it is outside because they're extracting heat from that air. The colder the air is, the harder it is to extract that heat. So when you use setbacks on a heat pump, you are asking it to work really hard when it is the hardest to work, which leads to inefficiencies. So this is why it's based on this and those other charts that I showed before that Efficiency Maine recommends find a comfortable temperature and leave it there. Leave it there 24/7. If you want to set it back a few degrees at night because you're more comfortable with it a little bit cooler, okay, but don't do drastic changes. You're going, I mean, you can for comfort, but don't think you're doing it for efficiency, because you're not. Okay, so then my last project that I'm going to talk about is a pilot that we're doing with whole home heat pumps. This is ongoing, so I don't have a lot to tell you about it, but I can tell you what we're doing. We are looking at existing homes that do not have heat pumps, that have some sort of existing fossil fuel furnace. We were focused on furnaces because furnaces use forced hot air, and heat pumps blow hot air. So we're specifically looking for drop-in units where applicable, and the application of ductless systems, and that distribution with multiple indoor units where applicable. So there are 19 homes that are participating in this throughout the state, 10 of which are manufactured homes and 9 of which are traditional stick-built. And in all of these homes, we have either disabled or removed the fossil fuel system. They do not have a fossil fuel system to fall back on. Some of the homes where the heat load of the home is such that the design load of the heat pump is not exactly where we want it to be. We talked about, it's important to size the heat pump for the load of the home. And in some cases, the configuration of the home, you can't quite get there. And in those homes, we put in a very small amount of electric resistance as an emergency backup for those coldest days, just in case. And while I don't have any results to present at this time, I can tell you anecdotally that we have not seen a lot of electric resistance use, and we've had some really cold days. Because I love participant quotes. So here's some more participant quotes. You can see that one of these homes, it saw outdoor temperatures down to -20, and they're working great. That's it. That's my last chart.
Oh, fantastic.
That's fantastic.
Thanks, Laura.
Thanks
so
Sean
much. And Jonathan. Welcome you guys to come off mute. Yeah, like any good webinar, we are over time, we'll go a little bit longer, and then we'll send the recording out to folks just to let you know. A lot of folks were asking about slides and recording. We will send those both out probably tomorrow. I've got a couple questions, but Brian, you want to start us off?
Yeah, well, and Laura, maybe if you could stop sharing your screen, I want to touch really quickly on, because I know some people had some questions about incentives. So let me just really quickly touch on that. If you go to our website, electrifynow.net, you can find this Take Action page, and you can click on Install a Heat Pump here, and you'll get lots of information about how to do that in your own home. But I want to bring your attention to this button down here, this yellow one about IRA incentives, because I know that a lot of people are curious about that. If you were to click on that button on our website, it will take you to this amazing calculator from Rewiring America, or you could go directly there if you just Google Rewiring America IRA calculator, and you put your information in about where you live, the amount of income you have in your home, etc. And it'll tell you what sort of incentives are available in terms of tax incentives under the IRA plan, which is super useful. And you can also download, if you're interested there, this booklet on how to go electric, which gives you kind of step-by-step information on how to do all the things that we talk about in the world of electrification. So I just wanted to touch on that because these incentives are pretty amazing. Again, it depends a lot on your household income, but it could be as much as $2,000 in terms of tax incentives for a heat pump. And if you need some electrical panel upgrades or something like that as part of it, you could also see some incentives for that. So, all right, let's get into some questions.
Yeah, I've got one handy if you're
go for it.
And folks, obviously you're seeing 90 questions in the Q&A. Incredible. Thank you for that. We try to group them into kind of themes. And one thing that was coming through, and we had some earlier discussions on this, as a homeowner of an old mid-century home, someone wrote in the Q&A, is it best to make improvements to insulation before installing a heat pump system? I wanted to, maybe I'll ask you first, Jonathan, and then other panelists who want to join in as well on that.
Yeah, I think it's the thing about heating and cooling, especially in older homes, is it's kind of site specific. I can tell you, I live in a 1916 home, and we put heat pumps in and ripped out our gas furnace before we insulated and air sealed. And we then went back and did a home energy retrofit, and our house is more comfortable and our electric bills running heat pumps are less. But I think if you're you could have a house where you'll spend much more on a heat pump to achieve comfort. And if you insulate first, you'll need a smaller heat pump. And so it costs less to get the heat pump in. And that's why you really do need to have someone do what's called a load calculation on the house as built today, and then one with some of the improvements, and be able to make an intelligent decision. That being said, if your priority is decarbonization and you're on a budget, you get to choose. You could put in heat pumps first and then go back and improve. And when you do this with a cold climate variable capacity heat pump, I think you'll not trigger some of the consequences of having a heat pump that it might be relatively oversized if you reduce the load through insulation later. These variable capacity machines at least can adjust to that condition, whereas the older generations of heat pump can't. So anyway, I said a lot. I'll stop there.
Yeah, I think that's great.
This is a big question.
I mean, just, oh, sorry, go ahead, Laura.
Yeah, if I could jump in just super quick on that. We've run some numbers and done some analysis on it. And in most cases, dollar for dollar, you're going to have a bigger impact and a larger carbon reduction putting in a heat pump than you will insulating. I'm not saying don't insulate, but if you only have, $5 grand, 10 grand to spend, and you have to decide whether or not to insulate or put in a heat pump, the heat pump will have more impact in almost all cases.
That's interesting. Yeah, it's good to know.
Quick add to that. The load determines the capacity needed. I've got a friend in Denver, double brick house built in 1928. And, he's done some air sealing improvements, but it's still a pretty average brick home. And the heat pump he's got is doing the job. He's got a backup fireplace if he needs to seal combustion, but, got to do the math.
Yeah, I wanted to ask, that's great. I wanted to ask on that exact thing, because the load calculation seems to be a really central part of this. And, I think I know that if you have a good, competent contractor, they're going to do this. But if you're a homeowner, how do you know that the contractor you're working with has done a good job on load calculations? Is there any tips you can give to homeowners so that they know that they're getting the right thing?
I think the first thing to ask the contractor is, have you done a load assessment? Because you say a good, competent contractor will do that. That is not standard practice, actually.
Ask them to talk about their philosophy on the load calculation.
Is it something you can see? Can you ask them, can I see the load calculation you've done? It seems like even if they have a piece of paper to show you, at least then it's better evidence that they've done it, rather than just say, oh yeah, I did it. Is that a good question to ask?
I think so. I mean, there's Manual J, there's what's the other one? Res something or other, right? I mean, there's software and there's manual calculations available that should have a product that is displayable.
Great.
Yeah.
Well, on that note, of contractors, and I know that we talked ahead of time, Sean, you wanted to kind of mention something, but I want to give you a chance to do that and just talk about the workforce situation. What do we need to vastly scale up heat pump installations, nationally?
Yeah, I mean, a little bit of a soapbox here. I think that I will ask everybody that's still on this call, on this session, if find out what skilled trade workforce programs are in your area and promote them, support them. If you know somebody who's looking at a career change or getting into a new career, encourage them to consider the skilled trade. They're good jobs. They are well paid. They are, in my opinion, they're pretty future-proof, because we still need hands-on capabilities to interface with the digital and the AI future that we are heading towards, right? So I don't think we truly grasp the how underskilled we are as a nation and as a world for that matter, what we are heading into, right? The massive transition we're heading towards. And just like decarbonization, this is a must have, not a nice to have, it's a gotta have. And so please encourage skilled trade workforce development in your areas, whatever that might look like.
Any tricks from Efficiency Maine, Laura, on the workforce front?
You know, Maine has a really strong workforce when it comes to heat pumps. One of our biggest installers used to be an appliance store that saw what was happening with heat pumps and has completely transitioned their business. And they're now one of the biggest heat pump installers in Maine. And they are constantly recruiting, and they do a bunch of like on the job training and interning kind of things. So we have an incredibly strong workforce in Maine, which is why we're able to install 35,000 heat pumps a year in a state that only has 1.5 million people. So I don't know. I mean, Efficiency Maine does offer support to contractors. We have training scholarships. We have some equipment scholarships. So we are doing what we can to support the contractor community. But I think a lot of it is just the fact that we have a lot of demand in the state, and demand drives supply.
That's great to hear. I wanted to return to the dual fuel question for just a second, because the way, there's a lot of conversation about that. I think in a lot of places, in fact, here in the Northwest, the gas utilities are starting to promote that as a way for them, I think, for them to stay in business. But I just want to clarify, what I think I'm hearing from you guys today, which is that yes, dual fuel is a legitimate path if you have a heat pump that is not capable of achieving this cold climate kind of high capacity output. But if you have a cold climate heat pump, you don't necessarily need a dual fuel system, with maybe the exception, like you were talking about, Laura, of emergency heat strips, or maybe auxiliary heat units in a bathroom maybe that isn't well serviced by your airflow system. Is that correct? Is that fair to say?
That's what we're seeing in new construction in Maine. And retrofits. And homeowners have taken it upon themselves to get off of their oil system, and they've done it with heat pumps, or heat pumps with small amount of electric resistance. We've seen it. It can happen because it's happening.
From my perspective, the dual fuel solution is a transition technology. It gets us to 50 to 90 to 99% reduction of natural gas use, for example, over the next, for the life of that equipment. And 20 years down the road, 15 years down the road, when it's time available, the trade base is there, the cost structures have kind of normalized across heat pumps as a central technology, I think we'll see a very different picture.
That's helpful. Okay.
Yeah, I think with the dual fuel, the piece that utilities are concerned about, even in places that aren't that cold, is that their grid isn't as renewable full, and they would rather see a furnace burning natural gas at 90 some odd % efficiency towards heat, and instead of burning that gas to make electricity and having only be 30% efficient roughly. And so I think that's kind of some of the thinking that utilities are making, or at least the justification. At least thinking as a contractor, though, I mean, even in extraordinarily cold places, if you don't have enough heat from a heat pump and you think, well, I want to go to backup, the option is to put another heat pump in. And so my house, I had one large heat pump and it didn't make sense. And so I pulled off some of the heads on one large multi-zone and have 2 or 3 small heat pumps that do the lion's share of the heating. And then we turn on these other zones. So we have 3 heat pumps at our house. They're tiny. They don't make much noise. The smaller ones use less energy they have a greater efficiency.
I do want to comment on that, Jonathan, because I know there's some questions in the chat about this too, about well, aren't we trading off burning gas in our homes for burning gas somewhere else to make electricity that's less efficient and stuff like that? That's a myth that is very popular out there, that the gas utilities really will help to promulgate. But I think I brought your attention to that study from UC Davis at the beginning of the program, where they looked at every part of the United States, and in every part of the United States, a heat pump will produce fewer emissions than the most efficient gas furnace available. So that is just like kind of like out there as a thing, but and also remember that, the grid is literally getting cleaner every minute as people put solar panels on their roofs, as more community solar gets put up, as more wind, like driving around here in the Northwest, you can't drive on the freeways without seeing a new wind turbine being shipped to a new destination. So I think it's fair. I think everyone on this call should be comfortable to know that a heat pump is going to produce fewer emissions in any fossil fuel based system anywhere in the United States today.
We can only, as consumers, we can only control what we control, and it's up to us to put heat pumps in our homes, and then it's up to the utilities who are regulated by governments to produce less carbon over time. So I think there's a little bit of a circular argument that goes around with this subject of dual fuel. Put heat pumps in your house, heat with heat pumps in the coldest place, Maine. They can do it.
Yeah,
we can do it
that's
everywhere.
Yeah, and just to be clear, heat pump technology is capable of heating basically any building in any major city anywhere at this point. The technology is there. If you're looking at a dual fuel, it's because there are gaps that apply to your personal situation that you're just not willing to go to that next step, or maybe you can't go to the next step. I totally get that. Yeah. But I look at it as a transition technology, and the technology's already there when you're ready to make the move.
Love it.
Joe, we're quite a bit over time here. I really appreciate all this from our panelists. Any last questions, or should we wrap it up?
I think, I had a couple more. Let's do one real quick. Folks were interested on resilience. If the grid goes down, any thoughts on resilience and heat pumps to take us home?
Yeah, the first thing I would point out is that there are very few heating systems utilized in homes in the US that don't rely on electricity in some way, shape, or form. So if you don't have a generator and the power goes out and you have a furnace, you have no heat. If you have a boiler, you have no heat. The difference with a heat pump is that it will require a larger generator, and it will require a generator that provides good, clean electricity, right? It's got to have a good signal. So it does, there is a complication there, but it's people that are like, oh, you can't have a heat pump if you have power outages. How is it any different if you don't have a generator and you have a furnace? You're still not going to have heat. And I can tell you in Maine, where we are subject and prone to power outages, most homes have wood stoves because wood stoves do not require electricity. So that is a very popular emergency heat supply in Maine.
Yeah, it's part of a broader question of, what tools do you have to be resilient? And I will give you one story out of Colorado. Little less than a year ago, there was a major fire in Boulder County that took out 1,100 homes in 8 hours. It was the most destructive fire in Colorado's history. A friend of mine who is a passive house builder, he has a retrofit house that he's upgraded to passive levels, not specifically, built passive house. He was back in his house 3 days after the fire with a heat pump, with a cold climate heat pump, because the utility company was able to turn on the electricity to his block sooner than gas. Some people got into homes with electricity weeks before some of the gas was turned on. Now, I don't want to, say one thing or the other, but it enables you to be more flexible in more ways, I think, than relying on a system that the utility company might not even be happy to turn on, because who knows what's involved with that line somewhere along the line. And I just see it giving you more choices, not less.
I lived through the San Francisco earthquake in the late 80s and early 90s there.
We lost you, Brian.
It was the same thing. The electricity comes back on almost immediately. The gas took months. Okay, well, maybe we should wrap it up, Joe, because I really want to thank all of our attendees for hanging in there with us. And thank you again to all our amazing panelists. This has been fantastic. I learned a lot, and I really appreciate you guys taking time to tell us about all the good things that are going on in Daikin and Mitsubishi and in Maine. So thank you very much. And Joe?
Have a great happy holidays to everyone. Yeah, huge thanks to the panelists. And Brian, leave us with our favorite.
Yeah, so I appreciate all of you out there who are on your own journey towards electrification. We thank you and congratulations on what you've done, and good luck with all your electrification projects going forward. And feel free to contact us if you ever have questions. If we can't answer it, we will find someone who can. Thank you.
Thanks, everybody.
Thanks all.
Bye, everyone.
All righty, so we are 1 minute past the hour, so I think I'm going to jump in and start here. Hello, everyone, and welcome to today's webinar. We are thrilled to see this big and diverse group joining us to discuss HVAC choices for student health and learning. And thank you all for spending this hour with us. It is definitely going to be jam-packed. Before we jump into the webinar, I wanted to start with a couple of announcements for you. First, please be aware that the audience will stay muted throughout the webinar to avoid any mishaps. But that being said, we would love to hear from you during the webinar. Please type any questions that you might have into the Q&A box, which you can find at the bottom of your Zoom screen. And you can leave questions for us at any point during the webinar, and we'll hold them to answer until the end. And then lastly, this webinar is being recorded, and you'll receive a link to the recording by email when it is ready. Next slide. So my name is Emma Hines, and I'll be one of your moderators today. I am speaking to you on behalf of RMI, formerly Rocky Mountain Institute. We are a nonprofit organization working to accelerate the clean energy transition. And I work on a really unique team here focused on the health benefits of transitioning away from fossil fuels in our buildings. And I'll pass to my partner, Sarah Ross, for a quick introduction now too.
Great, thanks, Emma. My name is Sarah Ross. I'm a co-founder at Undaunted K-12. Undaunted is a national nonprofit with a mission to support America's K-12 public schools to make an equitable transition to zero carbon emissions, while also preparing young people to build sustainable futures in rapidly changing climate. Thank you so much for being here with us today.
Thanks, Sarah. And we are also very lucky to be joined by 3 speakers today. Each will introduce themselves in a little bit more detail, but as a quick overview for you all, our speakers today are Dr. Erica Etland from Perkins & Will, Wyatt Ross from CMTA, and Julia Casagrande from the New York City Mayor's Office of Climate and Environmental Justice. Next slide. So before I pass to each of our speakers who are going to present on pretty distinct subject matter, part of my role here today is to provide some introductory remarks and a little bit of context to help construct a cohesive narrative between the 3. So to make sure that we're all on the same page and have a basic understanding, when we talk about HVAC systems or HVAC, we're talking about the heating, cooling, and ventilation equipment that's used to keep the air in our buildings a comfortable temperature and humidity and clean from any pollution or viruses. And there are 3 big motivators behind this webinar, and these have also underpinned Sarah and I's work on this for the past year and brought us together in the first place. So to walk through those, the first motivator is increased attention. So you probably all know that we are now officially 3 years out from the onset of the COVID-19 pandemic. And if there's one thing that has been reinforced yet again, it's this critical role that HVAC equipment plays in schools for disease mitigation and how school leaders can select the best equipment for that and beyond. The next motivator is increased need. So COVID is obviously still a great example of this, but to pull another one, we've also been seeing the impacts of school closures and lost learning time from extreme heat, especially in schools lacking cooling. And this is going to continue to be a problem here in the US, demonstrating a really clear need for all schools to have adequate cooling in place. And then finally, the third motivator for us being here today is increased funding. So we're recognizing that we're in this moment where that increased attention and increased need are being met with a new funding landscape, with more than one source of funds like the Inflation Reduction Act and ESSER funds as well. And this is allowing states and jurisdictions and school districts to invest in their HVAC systems, making it important that we get those investments right. Next slide. So over the past year, Sarah and I have worked to solidify our thinking on this topic and to also make something of our desire to educate and advocate for cleaner and healthier schools. So we did what most folks do, and we wrote a report, and it was published back in January. So we're using this webinar to uplift its messages again, but also the voices of our 3 expert guests today. There's one more nugget from this report, though, that carries over into the naming and framing of our webinar here today, which is the title of having choices when it comes to our HVAC systems in schools. So we set up a framework in the report of legacy and modern HVAC equipment. And it's important that we communicate with you all here the distinctions between these two, because you're going to hear us and our speakers talk about the importance of transitioning from that legacy to modern equipment. Next slide. So let's start with legacy HVAC equipment. These systems rely on burning fossil fuels. That can be things like gas, oil, or propane, and they're burned on site in our school buildings to make heat, which is a relatively inefficient process. Some common examples in the school environment are systems like boilers and central packaged units. They may or may not be supplemented with air conditioning, and many don't accommodate advanced ventilation and filtration. It's also really important to note that when we say legacy, that we're not necessarily talking about the age of the equipment, but more so about the approach to making heat. So a brand new gas boiler is still in this legacy camp because it uses this outdated and inefficient approach to keeping buildings comfortable. Next slide. On the other hand, though, modern systems, instead of making heat, they move heat that already exists in the air or in the ground. And by using this approach of moving heat, we can both heat and cool our indoor spaces with just one really cool piece of equipment, and that's called a heat pump. This approach doesn't involve combustion of fossil fuels. It can be powered with clean, renewable energy, and it's vastly more efficient than burning fossil fuels, and it does a better job of ventilation and filtration. This transition to modern equipment is already happening in leading schools today, which you'll hear about in a little bit, and it really is the future for all schools. Next slide. So I'll wrap up this background by sharing that there are 3 key messages that we want to deliver in today's webinar, and each of our guests will speak on a portion of these messages. So the first big one is that transitioning to modern HVAC systems is critical to student health and learning. Our second message is that over the past few years, and especially now with the passage of the Inflation Reduction Act, that the economics are changing in favor of all electric and high performance HVAC options. And then third, which is really exciting, is that we already have fantastic examples of how states and jurisdictions and school districts are taking action on this transition. So now, with all of that background in mind, it is my pleasure to hand the mic over to our first speaker, Dr. Erica Etland, who is a true expert in connecting building quality to student health and performance. And she is going to dive deeper into this first key message for us. So take it away from here, Erica.
Awesome. Thank you, Emma. Hi, everybody. I get to be sort of today's hype woman, I think, which is, so my name is Dr. Erica Etland, and I'm the director of the Human Experience Lab here at Perkins and Will. And much of my research is focused on how K-12 buildings impact child health and really what do we do about it. So to kick us off today, I'm going to go into 2 critical questions. First, the why now and why HVAC. So we're going to get into it. So the first piece here is that this is not new. And this discussion of ventilation in K-12 is not really something we have ever left in our sort of discussion. You know, it dates back to reducing tuberculosis infections in the early 20th century. And yet, what's interesting to me when I look at these images from almost 100 years ago, we weren't able to radically change the way that we responded to this last pandemic. We had outdoor classrooms, we opened windows. And so on the next slide, it highlights the fact that this is, you know, our buildings need to be thinking about this radically, and that as we modernize our K-12 buildings, that this isn't just sort of improving air quality for a pandemic, it's even looking right before. So if we think about 2019, we had a measles outbreak that spread through coughing and sneezing. This impacted 22 states at the highest level since 1992. Then we see that this is an equity issue. And so we're also recognizing that there's just persistent inequities when we think about asthma, which is one of the largest determinants of chronic absenteeism. And then we just have seasonal issues like, seasonal flu that is impacting 18 states also in 2019. So as I go through this and I think about, well, why now? On the next slide, it's really about getting into the data. And so we have growing evidence that our K-12 facilities are in need of replacement or repairs. And, if we look at this 2020 congressional report, what we see is that 54% of public school districts needed to update or replace multiple building systems, but 41% of school districts needed significant HVAC system updates. And so this is equivalent to 36,000 schools nationwide. So this is a really important time for us to think about, well, what is this evidence and what do we do about it? So next, let's get into the sort of why now from a human side. We all fall into the trap of maybe prioritizing the building, but it really comes down to people. And so when we think about improving our students' environmental quality, it's going to have lasting impact on their growth and development. So every decision we make now actually helps when we think about the fact that by the time our students graduate 12th grade, they've spent 15,000 hours in their school building, their lungs have continued to develop and sort of function in a certain way. We know that kids are breathing 50% more air. And so all of these aspects are leading to sort of an increased susceptibility that we need to be thinking about. This isn't just an office building. This is really something where the people who occupy this space make this an important priority. And so on the next slide, we talked about, well, what is that growing evidence and research? Well, back in 2017, with the Healthy Buildings team at the Harvard Chan School of Public Health, we started to dive into what were the 9 foundations of a healthy building. And what we found was ventilation, air quality, thermal health, dust pests, all are having radical impacts on our child and teacher health. And so this was sort of an early framework for us to think about. And I would say through the pandemic, we've had the ability to maybe expand it to other social and emotional, holistic health perspectives. But for today, I want us to just get into this. So on next slide, we see that we have this incredible report that kind of does all the synthesis for you. So if you're enthusiastic about acoustics, by all means, knock yourself out. But we found out that what was really important is that there's this incredible body of research that goes beyond even our RMI report, but allows us to really understand what happens if we don't make these health-based decisions. So basically, on the next slide, what we see is that there was a central thesis of this document, which was that health is actually foundational to student thinking and performance. So for every day that a child is in a classroom that's too hot, too stuffy, there's direct impacts on their ability to focus, to be attentive. And so at the end of an academic year, what are you really measuring? Are you measuring sort of their actual ability, or is it sort of being influenced by the student's environmental conditions that are impacting those test scores? So this is sort of why this is relevant, but I want us to get into why HVAC specifically. So if we get into this, what we see is that there's actually lots of sources of these indoor air quality pollutants, and it's everything from the furniture and what chemicals are in our products. So if we think real micro, thinking about viral particles like, seasonal flu or COVID, we also bring in other, common pollutants. This can be things like our adhesives, our supplies, and then it gets into stuff that is driven by our building. So it could be our school occupants, so the building as itself. So thinking about on-site combustion, when we think about some of that legacy HVAC aspect to it, we also see that some of our past building materials have migrated into the dust, creating this legacy pollutant situation that we need to be thinking about. We have seasonal pollutants, things like allergens, pollen, even just wildfires that we know can track across the United States, and then even the siting of the building. Is it located close to traffic, major airports, other sort of waste sites as well? So these are just important factors for us to be considering of, okay, there's the soup around us, and how are we going to respond? And that's on our next slide, is really thinking about ventilation and filtration as a true spectrum. So there's three main goals of ventilation. One is to just control and remove some of those airborne pollutants. The second is to dilute indoor air with fresh or clean air. And that's the assumption that the outdoor air is cleaner than our indoor air. And then the third is managing temperature and humidity. So these are opportunities for us to think that it's not, well, do you have ventilation? There's lots of, nuance in that conversation that we'll get into today. But again, focused on health, if I think about the next slide, what we see here is that, again, that foundational piece. We know that when we underventilate our classrooms, we have increases in viral infections, increase of wheeze, sick building syndrome symptoms, even just satisfaction decreases. And with that comes, decrements in attention, comprehension, concentration. So no wonder then we see that there's impacts on our standardized tests. And I love this study on the next slide, which is just basically saying that a poorly ventilated classroom is equivalent to a student skipping breakfast. And yet we have universal breakfast, programs across the US to fill that need because we know it's important. And so to me, some of this work really gets down to an equity piece. So if I look at the next slide, what we see is that African American and Hispanic students, as well as free and reduced lunch students, are experiencing high levels of indoor temperature. So this isn't just about sort of the pollutant side, it's also about the temperature that they're taking their tests. And so what we find is that they're compared to their white Caucasian counterparts or their more affluent counterparts who are typically in that optimal temperature for test performance, we see that there's this discrepancy. So when we talk about HVAC, it's really also an equity piece. And so to kind of nerd out a little bit more on thermal comfort, on the next slide, one thing I would like us to sort of start thinking about, and this was really critical in the Healthy Buildings work at Harvard with Joe Allen, was really shifting our conversation around thermal comfort, which is really just a subjective measure of, how hot are you in this space? Are you comfortable in this environment? And really acknowledging that children have higher baseline metabolic rates, they have higher core body temperatures, their ability to acclimatize is not the same. And so when we even think about, how some of these standards were created, like ASHRAE 55, we find that, they're not maybe meeting the needs of a very sort of active third grade class, perhaps, and that they were based on sort of men in three-piece suits. So we have to sort of shift our thinking to something around thermal health. And so this is an assessment that's bringing in some of those personal factors, clothing and metabolic rate and physical activity. So on the next slide, we're jumping into the fact that, we see that there's this U-shaped relationship, that there's also cold stress as well as heat stress. And so being able to provide both heating and cooling in our buildings is critical, because when we see that we kind of go to those either extremes, there's impacts on, our memory, our reasoning, and our skills that make us sort of more susceptible, and especially young students. And to me, on the next slide is really when we think about it in the context of climate, that there's this important piece here, which is that in a study of 75,000 students, they found that students taking an exam on a 90-degree day versus a 75-degree day were 12% more likely to fail that exam. And so this is equivalent to the Black-White achievement gap. So we have a real important focus here, where if we think about the average life of a school building, how many 90-degree days are in our future? And so with that, I want us to kind of get into the action. And so that is it for me. So thanks so much. On the next slide is just my contact info and some other resources. And we get into indoor air quality a lot more in depth on a podcast called Inhabit, which is a Perkins & Will production. So thanks so much.
Thank you, Erica, for giving us an all too quick dip into this really deep body of research that connects the built environment with our human health. So now we're going to hear from Wyatt Ross. Wyatt is an energy and sustainability engineer with CMTA. CMTA is recognized as a national leader for delivering high-performance sustainable projects. Their portfolio includes the first net zero school in the country, Richardsville Elementary in Kentucky over a decade ago. It also includes more recently the first, as far as I know, net zero school retrofit, Buckley Elementary in Connecticut. And it includes the first building to combine WELL certification and net zero, which happens to be CMT's very own headquarters in Louisville. So Wyatt, thank you so much for being with us here today in Brian's stead. Where should we start?
Yeah, great. Thank you so much. So happy to be here. Good afternoon, everybody. So in addition, to talking about the health benefits and performance ramifications of our HVAC systems, we also want to talk about the environmental impacts that our HVAC systems can have in our schools. And so today I want to talk a little bit about what these modern systems look like in juxtaposition to kind of this legacy equipment that we're talking about, and what that means from an emission standpoint from our buildings, and then also what are some tools and some recent legislation that we can leverage to help achieve and implement and deploy these systems. So if you jump to the next slide. So with these modern systems, kind of a core concept that we're looking at here is the concept of electrification. And so when we're talking about electrification, what that means is it's the switching of utilizing combustion on site in our buildings to generate heat as it relates to HVAC, and switching to systems or technologies that are fully electric. And the reasoning behind this is that when we switch our buildings to utilizing systems that are electric, eventually we can depend on renewable energy such as solar, nuclear, wind, hydro, to generate that electricity. And the benefit that has, not only at the building level, but at the global level, is that transition will allow us to use less greenhouse gas intensive fuel sources that you see here on this slide. And it also will decrease the amount of air pollution that we're seeing both at the building level and our local community level, and also at the global scale. So if you jump to the next slide. For the most part, when we're talking about the fuel sources that we're utilizing for generating heat in our buildings, whether it be boilers or packaged rooftop equipment, we're typically talking about natural gas. And so what you can see in that purple bar there is when we combust this gas, it has a significant greenhouse gas impact, which contributes to climate change. And then in addition to combusting that natural gas, there's also what we call fugitive emissions, which are associated with the leakage of natural gas as it's distributed to your building. And so if we can remove these systems or the use of these fuels from our buildings, we can make a tremendous impact on reducing our overall carbon impact. Next slide. So we talked a little bit about legacy versus modern equipment. There's kind of 2 points that I want to make. And so when we're talking about legacy equipment, to Emma's point, these aren't necessarily old pieces of equipment in our buildings. It's more so that it's technology that is more traditional. It's been around, and it's not going to meet the needs of our schools in the future. And so we're talking about, hot water boilers, steam boilers, things that can't achieve the efficiency levels of some of the modern equipment that we're talking about. But it also could be electric heat, which is, resistant heat, similar to getting hot when you touch a light bulb, only going to achieve an efficiency of around 99%. The other downside of these legacy equipment, pieces of equipment, is that they can only generate heat, and we're coming into a world which will more and more so require cooling. And so this modern equipment, which we can more broadly classify as heat pump technology, has a couple of benefits. One, it's extremely more efficient, as you can see, 200 to 700% efficient, because it relies on moving heat rather than generating heat. And then the second benefit is that they can also simultaneously provide cooling. So they're more of a dual purpose technology. Next slide. And so when we look at comparing these technologies from an operational emission standpoint, because you're probably wondering, just because I electrify, where is that electricity coming from? There's still emissions associated with it. So what this is looking at is if we take a sample school in a region that has currently a fairly dirty grid, somewhere where that's using mostly coal-fired power plants to generate electricity, and we look at switching between a natural gas boiler that's generating heat at the building versus an electric heat pump, what are the total emissions of those two systems, including the emissions from electricity? And so what we see is over time, over a 30-year period, as we expect our grid to deploy more and more renewable energy and become cleaner over time, by the end of those two systems' life, a school that deployed electric heat pumps can expect to reduce emissions by almost 80% compared to a school that chose to use a natural gas boiler starting today. And so this just kind of gives you the sense of scale of the greenhouse gas emissions of an electrified new technology HVAC system can save. Next slide. So all that said, you still have to pay for these systems. And so how do we do that? And so, I think it's really important to be aware of the recent legislation that has passed. I'm sure most people have heard about the Inflation Reduction Act at this point. There's kind of two big things that I want you to take away from the slide, and then you can use the rest as a text as a reference. But the big thing is that before, in the recent past, these tax credits have been available in some form or another, or they have existed, but they have not been available to public K-12 schools. And so that has changed with this legislation. And so now there are incentives available that can help cover the cost or any premium associated with these modern technology. And then the other big change is that for some of these technologies, the tax credit base has increased from 10% in the case of geothermal heat pumps up to 30%. And there's additional incentives that can potentially raise that. And so what that means is that not only can these heat pumps, to modern technologies, meet a lot of the technical needs of heating and cooling, but they can also meet some of the financial needs that districts are facing. Next slide. So again, we won't go into all of the technologies that are covered by this bill, but really the big one for our conversation today is ground source heat pumps. Also solar photovoltaics are covered, battery storage, some microgrid technology, and a whole slew of other technologies that we won't have time to get into. Next slide. And so just real quickly, I wanted to jump into, kind of a case study. This is a school that Sarah mentioned that we worked on in Connecticut, net zero energy renovation. It did not leverage the tax credits, but this is kind of a case study to prove out what it would have looked like if they had, how beneficial that could have been. And so this is a life cycle study over life cycle cost analysis over 25 years. And you can see if we just compared to a code minimum system that we could have deployed, it would have cost roughly $13 million over the course of that system's life to own and operate. And so if we compare that to the geothermal system that they went with on the next slide, you can see that we were able to provide them with a system that had almost a $3 million savings over the course of the system's life. The only downside is that it did have a small premium associated with going with that HVAC solution, and that was going to result in a 6-year payback. So if we jump to what these new tax credits could have done for the financial story of the system, is that it would have resulted in a 34% tax credit that could have covered 34% of the total cost of the entire HVAC line item associated with the system, and reduced the 6-year payback to 1 year. So almost an immediate return on investment, and saved $5 million over the course of the system's life for that district. And so the key takeaway here is that with these tax credits, one, before the tax credit, this HVAC system still made a lot of sense and had a lot of merit for all the health reasons that Erica was talking about, as well as the energy savings associated with the system. But with the tax credits, it almost becomes this no-brainer, first cost, best option, and then all of those ancillary benefits as well. And so this just shows the magnitude of impact these credits could have for looking at these options. Next slide. So quick, sustainability playbook here. How do we actually go about achieving and implementing these systems? And so when you have a project come online where you're looking to maybe do an HVAC retrofit or new construction or whatever it may be, kind of step one is that we really need to make sure that we're asking for the right qualified people that can design and deliver these systems. And so including language in our RFPs that talk about performance outcomes, whether it be the health and wellness outcomes, the energy savings, the system types. If you're asking the right questions in the RFP, you'll bring people to the table that can deliver those solutions. The second thing is during design, design of any school can be messy. And so you have to have advocates both on the design team side with the architect, the engineers, structural contractors, and on the school district side that can continue to ask the right questions, make sure that we're talking about the right things and that we're focused on achieving those objectives that we talked about today. The third thing, and this one's really important, as we transition to more and more modern systems and away from traditional systems where contractors and estimators are more familiar, that transition can be a little bit of a pain period. And so estimators, if they aren't super familiar with these new systems, you might see them put in some buffer or safety factors associated with the cost of these new systems. And that can kind of inherently price out these systems, maybe unintentionally. And so what we want to do is make sure that we're getting early pricing sets that are very detailed, kind of dig into the weeds and make sure that we're getting the right information so that we're not making any assumptions that might be wrong, and falsely price out systems that we would like to keep. So the last step is then managing costs. And so I said it before, Buckley was able to achieve the geothermal HVAC system with a dedicated ventilation system and all these additional benefits before these ITC tax credits through the Inflation Reduction Act. So there are ways to keep projects within budget as long as you're prioritizing the right things. So if we're aware of what the goals and the systems that we can deploy, we can prioritize those in and almost always make it work. And then on top of that, we now have these new financial resources and incentives that can kind of be icing on top to make these more feasible. And that's it for me.
Perfect. Thank you so much, Wyatt. So now that we've heard from Erica about the importance of HVAC systems in schools and Wyatt about electrification and how the Inflation Reduction Act is reimagining the funding landscape for all electric retrofits, I am really pleased to pass the mic to Julia Casagrande, who will be giving us a behind the scenes look at New York City's recent and powerful commitment to electrifying schools. So take it away from here, Julia.
Amazing. Thank you so much, Emma. And it's great to have all of that information from Erica and Wyatt. I'm excited to dive into how New York City is working to electrify our schools and how we're navigating the different laws and priorities that we have in this space. So about me, my name is Julia Casagrande. I'm a policy advisor at the mayor's office. I work on researching and developing policy for New York City in the building decarbonization space and in the climate retrofit space. We've worked on developing policy like Local Law 154, our all electric new buildings law, and our clean construction executive order. But I also work on coordinating and advising city agencies that are doing decarbonization work, particularly when there are multiple agencies involved. And that's what I'm going to get into today on the school electrification front. So next slide. I was just going to give a little background on the New York City school system. We have over 1,400 school buildings in the city, and that's the largest school district in the country, and then also the largest contributor to municipal energy use within the city. So this chart on the right shows that K-12 schools are 32% of our municipal energy use, and it's also our largest source of municipal greenhouse gas emissions. I would note these buildings are old. We're talking about legacy systems that may or may not be new. In this case, they are largely very old boilers. We have old electrical systems. We have old envelopes. We have a lot of historic buildings that are 100 years old and they are registered historic sites. So it's complicated to retrofit these buildings. That being said, our school construction authority and our Department of Education have been doing a lot to reduce the emissions of our buildings. As of 2007, we have all our new buildings following Green Schools Guide, which is the New York City Schools specific version of LEED compliance. And we have about 10 to 15 new schools that are built each year and have been following this since 2007. Obviously, it's been updated a lot of times since then. We also have a lot of efficiency work that's been going on. So across the portfolio, the municipal portfolio, the city has reduced emissions by 26%. And then there's a lot of innovative work with green roofs. We have a net zero school in Staten Island, PS62R, increasing amounts of solar, etc. But there's still a lot of work to do in this space. A lot of the improvements to date have been from like fuel switching and the electrical grid cleaning up. and there's a lot of work to do. So what I was going to highlight is we have 200 schools remaining, about 200 schools remaining that are burning number 4 heating oil and emit very relatively high amounts of air pollution. So that's sort of the universe that we're focusing on for this electrification initiative, and I'll go into that more on the next slide. So in the landscape, there's also some competing laws and priorities that are relevant to the policy decisions that we came up with. Fuel oil 4, I don't know, depending on where folks live, may or may not use this fuel, but it's a heavy residual fuel oil and it emits high amounts of air pollution. The phase out of fuel oil 4 was required by 2030. When we set this policy, we actually just last month passed a law that's accelerating this phase out, and now it's going to be required by 2025 for schools and 2027 for the private sector. We also have biofuel heating requirements, which are state mandates. There's city mandates, but then the state mandates are more stringent than city. So that's what we're following. We're going to be having to use 10% biodiesel by 2025 and 20% by 2030 in all of our heating oil. We also have Local Law 97, which is our building performance law, and there's requirements for private buildings, which gets more press, but we also have municipal operations requirements that are actually more stringent. We have to reduce our municipal portfolio emissions by 40% by 2025 and 50% by 2030, and that's from 2006 levels. The last law I would note is Local Law 154, which is our all-electric new buildings law. We have all schools will be electric by law as of January 5th, 2025, but they're already building all electric schools at this point. I would just also note that there's all these laws that we have to comply with, and then there's also our priority, which is to make sure that we're focusing on improving air quality and delivering benefits to New Yorkers, particularly in neighborhoods with high asthma and those that have borne the brunt of environmental injustice in the past. So on the right here is a slide that shows the discrepancy of asthma emergency department visits from air pollution in New York City. So we have Northern Manhattan and the Bronx really, and then some in central Brooklyn really feeling the brunt of that. Next slide. Thank you. So with all of that in mind, we needed a plan to get our schools off of fuel oil number 4 and also to leapfrog to electrification to meet our decarbonization requirements. So we did not want to do any more replacement in kind, putting in new natural gas boilers that would replace fuel oil boilers. We definitely wanted to focus on electrification. However, we have 1,400 schools, so we couldn't electrify them all right away. So in the fall, Mayor Adams announced the Leading the Charge initiative, which is a $4 billion commitment to electrifying existing school buildings. And we have 100 schools that are be electrifying by 2030. You may remember from the earlier slide that we have 200 schools that are burning number 4 fuel oil. So what we decided to do was no new boilers. We are retrofitting the existing boilers to comply with the short-term regulations for to phase out number 4 fuel oil and have the biodiesel contents, and using our capital, our big dollars to install heat pumps. So we're doing an operation and maintenance retrofit on the existing boilers, get the quick air quality benefits at a much lower cost, and we're focusing the big dollars on our school electrification project. Also note that we're starting in communities. We prioritize communities with high asthma rates, as well as a heat vulnerability index and high truck traffic, which just adds more pollution to the area. Next slide. So I just wanted to speak a little about the collaborative strategy that we used to get to this agreement. Within the government, we have our Office of Management and Budget, who committed to not funding new boilers. So they really decided where the money was going to be going, and that's how we got the commitment for the electrification. Our school construction authority and Department of Education worked super closely together to figure out the technicality of these conversions. As I said, our buildings are really old. It's difficult to retrofit them. So these teams worked really closely together on the technical aspects. Our Department of Citywide Administrative Services oversees our portfolio of energy use for the city at large. So we worked with them, and then our office more on the policy and advising. We also we've had a lot of support for this initiative. Environmental justice groups, labor unions, and community groups have been advocating for school electrification way before this announcement was made. There was a Creating Green Healthy Schools initiative that was directed specifically at the mayor's office to implement changes such as this. Of course, there's more to do, and they continue to helpfully push us to go further. But largely, we've gotten a lot of support in this area, and I just put some screenshots of tweets there. On expected outcomes, we saw a huge air quality improvement from when we phased out number 6 heating oil, which was the prior phase out. This was completed by 2016. From that phase out, we see an annual reduction of 1,200 tons PM2.5 in the air around New York, and that prevents 210 approximately premature deaths annually. We expect this trend to be continued with the accelerated phase out of fuel oil number 4. And in prioritizing environmental justice areas for electrification, we want to make sure that these areas have the additional benefit. And we will see a reduction in air pollution and improved health, and keep New York City on the path to meet our climate mandates through leapfrogging to electrification. Just note, like, the city has a lot of power in where we spend our money, and we see this as a $4 billion market signal over 8 years towards electrification and decarbonization. So we're hoping this will help spur the market in New York City to have more contractors on board to do the work. And that's all I've got.
That was awesome. That was awesome. Thank you so much, Julie. The work that you all are doing in New York City is really nation leading, and we're so thrilled that you could share it with the audience today. We hope these panelists have inspired you all to think about what is possible in your own communities. After all, there is so much to be gained. You can read more about the 6 benefits of moving to all electric high performance systems in the paper. Our speakers touched on almost all of the benefits here today. And so right now, I'm going to assume that you're with us and that you are compelled and that you are ready to move to action. So let's go to the next slide. The report has a recommendation section at the end that is organized by role. So are you a state policymaker? Are you a school board member? Are you a parent? We've offered our thoughts on how you can champion the work from wherever you sit in the world. So please take a look at those recommendations. So I'm actually going to focus now on the potent moments for intervention that we cannot afford to miss. The first is new construction. New construction is one of those rare opportunities when we hold the responsibility of making good 50-year choices. So we really need to ensure that all new construction incorporates this modern HVAC technology. This can be a challenge, right? As Wyatt mentioned, there are contractors and some design partners that are frankly more comfortable with how they've been doing things, this legacy equipment, and change is hard. So if your community is building a new school, make sure your town leaders are clear on the importance and benefits of embracing these modern systems right from the start of the process. And make sure your design partners are also on board, or it will be very difficult to move in this direction. The second potent moment that we need to have our eyes peeled for is systems replacement. HVAC systems reach the end of their useful life and need to be replaced. The key here is to avoid what we call a like-for-like replacement. And instead, we need to make a break for this modern equipment. And again, here it's about establishing modern HVAC systems as the goal early on. We can't wait until systems fail to have the conversation. At that point, it's an emergency and we're destined for a like-for-like replacement. And the last opportunity is really about facilities planning. Our facilities plans that actually too few of our schools have need to reflect this desired transition from legacy systems to modern systems. These plans are sometimes called decarbonization plans when they absorb this lens. And our partners at New Buildings Institute have a great tool for that work that we will put into the chat for you all. Next slide. So with those 3 points of intervention in mind, we've all got work to do. And we've got 2 easy to digest one-pagers that you can use to open the conversation with leaders in your town. One is on the big ideas, right? A non-technical set of guideposts for really building understanding and therefore confidence in this area. And the second is a one-pager that recaps these 6 benefits of modern systems. So please use these as conversation openers. They are available on our website that we'll put again in the chat, so it's handy for you here. Next slide. And lastly, before we get to Q&A, I really want to recognize all of our wonderful supporting organizations. We have a stellar audience here today, largely because they helped us get the word out. And we are particularly appreciative of the organizations who contributed staff time, our advisors. We had a wonderful set of advisors on this paper, our leading contributors in the field, and we are so grateful that they devoted time to improving our thinking and our writing on this topic. So a big shout out to ASHRAE, the Center for Green Schools, the Collaborative for High Performance Schools, CMTA, New Buildings Institute, Perkins and Will, and Stanford. So thank you so much. So it's time for your questions, and I'm going to exercise my moderator role here and ask the first one. So for each of our panelists, in 30 seconds, this is your short little sound bite. Tell us what is the most important thing that you want the audience to take away from your presentation. And we're going to go in order. So Dr. Etland, Erica, you are up first.
Awesome. So, I think one thing that became really evident from the chat is that HVAC is a part of this, but it is not the whole solution. And I think we have to really be thinking about, especially when we're talking about equity, that we take sort of this look at the hierarchy of controls and where is HVAC a part of the solution, but recognizing that all buildings are not going to be able to kind of get to the Ferrari of HVAC systems, that we need to be able to sort of think about where does behavior change come in terms of energy conservation, where does it come in terms of reducing, asthma triggers. So I do think there's, just something that I feel very strongly about that's coming through the chat is that it's not just about outdoor air pollution, it's about the indoor. And I think that's where sort of the human behavior side complements some of these HVAC decisions. And then real quick, coming from an architecture firm, I think it's really important that you see yourselves as advocates to hold them accountable, to make sure that they're giving you the life cycle costs, that they're really trying to sort of work dynamically with people like CMTA and having the correct engineers on the job to make sure that they're providing sort of the full energy savings. Because I know there's some back and forth that health is, wow, we're talking about health first and not about energy, but I do think it's so often forgotten about what we're really trying to get to. And it is so foundational to sort of the main purpose of a school. So let's think holistically about all of this.
Great. Wyatt, that was Erica's 30 seconds, maybe. What's your 30 seconds?
Great. Yeah. So I guess 2 things. One, I think it's really important to take away from this conversation just how important HVAC systems are on the impacts of health, wellness, thermal comfort, thermal health, emissions, energy cost savings. I think a lot of times HVAC can kind of be an afterthought when it comes to designing our schools. And so hopefully a takeaway is that, there's actually really important implications to what types of decisions we make as it relates to HVAC. And then, the second thing is there's a lot of things in the chat about consultants saying no. One of the things that I would like to say is, it's your building. You need to really push. If someone is telling you no, they probably have not done it before. These are not, bleeding edge technologies. These are things that have been around a long time. There are ways to make these solutions work. almost always. And again, it's not going to happen designing in a vacuum. It does have to take into account energy efficiency, or else you're going to pay out the nose for a lot of heating and cooling you don't need. But if you can do envelopes right, if you can make other improvements to the building, you can make these things pencil out. And so you need to be, it's your building, you're paying for it, and really leaning on your consultants to give what you're asking for is a key thing.
Awesome. I love it. Julia, your big takeaway for the audience here.
Sure. I would just say from our perspective in New York City, there's so much work to do. There's so much work being done all the time. And I think this project and this initiative has really highlighted that, like, when money is being spent, we need to make sure that it's being spent in the right areas. So putting the big dollars in electrification, and then prioritizing where we're doing it so that we actually make sure we see the biggest improvement in air quality indoor and outdoor for the folks who have the biggest impacts of asthma. Yeah, that's what I say.
Great, Emma. Well, I'm going to pass the baton over to you. Do you want to start us off with the next question from the audience?
Sure thing. So this first one is actually for Erica. So going back up to the top here. So we all know that you are a public health scientist and that you've been applying your expertise to K-12 school design for many years now. So this audience question was asking you to reflect on how often and whether the concepts of electrification and decarbonization more broadly come up in these conversations when we're talking solutions to the health and performance concerns that schools are facing. So from your experience, does electrification and decarbonization come up? If not, how do we bridge that gap?
I would say that we're at a point right now where those topics are coming up a lot more than health is. I would say that health is not as easily quantifiable as energy and cost savings. And so it's more of bridging our gap to be thinking about what are the health ramifications and what makes the most sense for our communities. I think this is something where we can talk about decarbonization, but it kind of gives me a little bit of like a back to the 70s where we had an energy crisis and we started removing all of our windows from our classrooms. And so we really have to be having sort of a holistic conversation about health. And that's why I really feel, and I appreciate sort of me getting to go first, in the sense that if we're going to have a conversation about decarbonization, we also have to be thinking about this in terms of climate adaptation and what are sort of the acute and short-term benefits of making some of these changes and investments, that it's not just a sort of a payout long-term down the line, but also things that, especially with schools across, New England and even to Cincinnati closing for extreme heat, we know those things will be felt pretty quickly. And it's an equity issue too. Who gets to have a decarbonization conversation is not for everybody. And so it is about how we're going to kind of lift all boats as we're talking about this.
Great. Why I've got a question for you, and it builds on some of what Erica was saying earlier too. So, when I think about districts that are building new schools right now, I mean, here I am on my high horse talking about how we can't miss this opportunity. And yet, as you know, probably better than anyone in this room, construction costs are really high, right? And community leaders are understandably sensitive to increasing tax bills. What would you say to a school building committee that is contemplating a gas boiler in new construction today as a response to those, very real, very challenging fiscal considerations? I mean, Erica talked about a Ferrari. Can we afford the Ferrari?
Mm-hmm. No, it's a great question. And, there's some legitimacy to that question. And there's also, there are things happening that, you can be wary of, so you can avoid ballooning costs that, may be more figurative than literal. And so, I would say first and foremost, I think there was a lot of great observations in the chat about energy conservation and other things that can be implemented into design so that you're, right sizing HVAC systems. So you may not need the Tesla Cybertruck to get the job done. You might be able to get a Nissan Leaf or something of that nature, a more economy electrified system to meet your needs. And so, first and foremost, when I talked about managing cost, I think that's a big part of it. Are your consultants, is your design team, are you as owners engaged in a conversation to figure out how to shift costs around so that you can, make an economic decision. The second thing is, the reality is that there is inflation in the construction market right now, and costs are ballooning, and being able, in decades past where you really could almost always keep these systems within budget, that can be tougher to do right now. And there is a premium associated with these systems. And so leveraging the ITC, I can't emphasize that enough, these new tax credits that are available. You may not be able to go geothermal, and so your tax credit options may be limited. But if you can, if that's an option, if you have the land area, if you've minimized your loads enough to where you don't need as large of a well field as maybe you would for the standard construction, you can leverage those tax credits, and that can be in transformational as far as the financials of that project, making it the lowest first cost option. So I would make sure that you've explored all options if you're going down that route. The other thing that I would add is if you think about that 30-year time horizon that I said, where I showed a heat pump compared to a natural gas boiler. If you're putting in a boiler today, one thing that it's hard to quantify, but something to keep in the back of your mind is what will the regulation environment look like in 20 years, in 30 years, in 10 years? And so how could those regulations impact the cost of operating a boiler when you could have switched to electrified option and had more control over the pollution associated with that technology?
Thanks, Wyatt. So I think I'm going to jump in here and have us switch gears a little bit to talk about ventilation, since we've been heavy on the electrification side here. So Julia, if you'll join us for this question. The New York City commitment is very focused on electrification of space heating equipment, but as we've talked about today, ventilation is key to student health as well. So curious if you could give us a little bit of the details on how ventilation fits into this decarbonization plan, and how do you see electrification unlocking those complementary efforts on ventilation?
Yeah, of course. And there's a lot more detail of the actual retrofit plan than I could fit into 10 minutes. But the electrification projects absolutely include upgraded mechanical ventilation in classrooms and in assembly spaces. There's also, we understand the link between adequate ventilation and performance, and the school department makes sure that what we have is optimized, and what we're doing is providing more ventilation as we're moving forward. I would also note that these projects, I saw a lot of questions in the chat around efficiency, and the schools that we're working on to electrify absolutely include efficiency measures as well, to optimize the mechanical system. And then there's a lot of work that's being done across the board, again, around sort of optimization and right timing. So like if we're doing work on a roof, making sure that we're upgrading the insulation on the roof so that it has the maximum efficiency components, and same things with windows. When we have a new roof, we want to make sure we put in solar. So I think with a portfolio of this size, a lot of the work is around planning and strategizing how to make the best use of sort of existing work that will go on, so that we can incorporate ventilation, electrification, and efficiency as well.
Great. Thank you, Julia. Back over to you, Sarah. We might have time for one or two more questions.
Great. I guess I'll go back to Wyatt here for one more question on the cost side. Are the costs for Buckley that you presented, are those just for the ground source heat pump system, and how do you think about that within a broader cost environment? Like, were you able to deliver that project, which was net zero, a retrofit, and ground source heat pump? Like, how did the overall project cost per square foot kind of compare with a conventional approach?
Yeah, that's a great question. So the cost and the life cycle analysis I presented were specifically for the HVAC equipment. So I think, around $4 million upfront for the base case. And I think we ended up around $5 million. So about $1 million premium in total to upgrade to the HVAC system, plus geothermal, all the ventilation improvements, all the things that we did at that school when it was all said and done. And so the total construction cost, I think, came in around $27 million. I could be misquoting that. I'm not entirely sure, but I believe that's correct. So the well field itself was around $850,000 for that school. When you take into account what you're leaving behind when you switch to a geothermal system. So that's a big part of getting into the weeds of the cost estimate. You no longer need the boiler, you no longer need the cooling tower, you no longer need the natural gas service to the building potentially if you're fully electrified. There's a lot of things that kind of get reduced from those costs that can be missed. So all of those are factored in to the life cycle analysis, as well as maintenance cost savings, water cost savings, and then operational cost savings from energy savings, obviously. And then with the tax credit, in the case where we could have potentially, if this had happened a year later and Buckley could have leveraged the ITC, the way that is working, because I saw a bunch of questions in the chat about it. And so the reason that K through 12 public entities, they're tax exempt normally, the way that you can receive those tax credits is through what's called a direct payment. And so essentially what that's going to look like is the federal government is going to be cutting checks for the percents that you normally would have gotten from off of your tax bill. You're just getting that off of the cost of the system. And so there's a lot of guidance that's going to come out from the IRS here shortly, kind of explaining the details of how that payment process will look like. But that's the way that it will be implemented. And so that's how that would have impacted the front end financials of the system. Did that answer the question?
Perfect. Thanks, Wyatt. So you took us straight to the end of the hour. So I think that's our last question of the day. Thank you again to our three speakers for joining us, and thank you all for joining us as well. We hope that you are leaving feeling motivated to take action. Give that full report in our one-pagers a read, especially focusing in on those recommendations towards the end. We would love to hear from you too. So here are mine and Sarah's email addresses. We'd be happy to connect you with speakers if needed. And again, you will receive a recording of this webinar soon by email. So thank you again and have a great day, everybody.